Okay, so this lecture is on the topic of acid-base indicator compounds, or indicators. Indicators are essentially molecules that can be isolated from different places. Oftentimes, some of them are natural products. They can occur in vegetables and things like you might see in the produce section of your grocery store. But they're basically molecules or dyes that will change color depending on the pH of the solution. So the pH is oftentimes the important variable for our indicator, and that's certainly going to be true of the indicators that we're going to talk about here in this particular mini lecture, okay? So it turns out that the model for our indicator compounds, regardless of what the indicator is going to be, there's many different molecules that can serve as indicators, but our model for this is that we're going to treat our indicator compound as a weak acid, a weak organic acid. And because of that, we can write an equation that looks like this. Now, HInd, that stands for the indicator molecule itself. This is the indicator molecule. And we said that it's a weak acid, so it's got a proton that it can donate, right? So this reaction is nothing more than the proton donation reaction for our indicator compound. It's acting as an acid. It'll donate a proton to water to make H plus or H3O+. And in the process, we also make this compound, Ind-1. That's the conjugate base of our indicator, isn't it? This one has just been deprotonated. This one's got the proton, the H+. This one doesn't. So our indicator model treats the indicator as a weak acid. This reaction is almost like the Ka reaction for our weak acid indicator, isn't it? But because we're dealing with an indicator compound, instead of calling it just a generic Ka, I might choose to call it Kind for our indicator Ka. So it's nothing more than the Ka for the indicator. And if I wanted to, then I could take the negative log of that number and I would call it PKHIn or PKInd if you want to have the same lingo. Nothing more than the negative log of this Ka, okay? So interestingly, I'm just treating my indicator as a weak organic acid. Now, why is that going to be something that's interesting to us, okay? When we studied acids and bases and talked a little bit about buffers, we decided that by adding or removing H plus or OH, we could shift equilibria back and forth, okay? So let's think about that for a second. What if I have very, very acidic conditions, pH 2, pH 3, we'll just say arbitrarily here very acidic, a lot of this around. If that's true, which way would this equilibrium would shift? Well, if I have a lot of H plus, I would shift to the left, wouldn't I? Which would promote protonation of our indicator. Now, if I just have a tiny, tiny, vanishingly small amount of this, very low concentration, that would tend to do the opposite. I'd shift to the right. So by controlling this, I can shift left or right. Well, guess what? H plus, isn't that directly related to pH? It's related to pH. If I have very low pH, I've got a lot of this. If I've got a high pH, I've got a little amount of this. So you can kind of see that if I model my indicator compound as a weak acid, I can shift this equilibrium right or left depending on how much H plus I've got. And that's going to be real important here. It just so happens, and this is the cool part, that if the indicator is in this acid form or protonated, it will exist in one color, and if the indicator is in this base form, it exhibits a different color. That's what makes indicators special. They change color depending on the pH of the solution, because if they're in their acid form, they exist in one color, but if they're in their base form, it's a different color. It might be yellow and blue, it might be colorless and pink. There's lots of different options, but they always change color depending on which form they exist in. So, if we go to a very low pH and have a lot of H3O present, we force the equilibrium to the left, to the acid color. But if we go to a high pH, we force it to the right in the base color, and that's why it changes color, because we force this equilibrium back or forth. Okay. Now, I'm not being very quantitative in terms of what pH is key and crucial for going one way or the other, am I? I'm just referring to very low pH, very high pH. Okay. Well, it turns out that the PKHIn for the indicator is super, super important. Okay? It's super, super important. Draw some simple conclusions down here at the bottom of the slide. If the pH level is the pKa or PKHIn minus 1, okay, so the PKHIn, that's the indicator pKa, take that number, subtract 1. If that's the approximate pH, your indicator dye is going to exist in the acid color. Alternatively, if the pH of the solution is right about the PKHIn plus 1 or above, the indicator exhibits the base color. So the PKHIn is kind of like the midpoint, okay? And here it says if the HIND is about the same as the IND, this is the acid and the base, right? If the concentration ratio is about 1, you get a mix between the two colors. But if the pH is higher, the pH of the solution is higher, you get the base color. And if the pH is lower than the PKHIn, you get predominantly the acid color. And it really is ending up being as simple as that, okay? So to give you an idea about how this works, I guess visually, you can consider this compound, phenolphthalein, which is a really common acid-base indicator. The molecule looks like this. And here's our key equilibrium, okay? It's plus or minus 2 H pluses. This is the acidic version. This is the basic version. And it turns out that for this particular one, I think that the PKHIn is somewhere approximately around 8, okay? So we would expect the color change then to occur about pH 8. So if we're way below that, exhibiting the acidic color. If we're above that, exhibiting the basic color, which is pink. So if we actually put some of this stuff in a test tube, and we start to change the pH, what you can see is only the test tubes on the two on the far right exhibit any pink color, the basic color at all. That's because at pH 2 or pH 4, 5, and 7, we're way below the PKHIn. So almost all of our dye molecules exist in this form at the low pH. This is what we see when our dye molecules are exerted to lower pH, below the PKHIn. We force the equilibrium this way. Because the pH is low, we got plenty of H+, it forces the equilibrium back to the left. But on the other hand, if we go to above the PKHIn, we start to see the pink color dominate, don't we? These last two are above, the pH is above the PKHIn. And because of that, we start to deprotonate the molecule and it exists in this pink basic form. So it's an acid-base indicator. Another example is called methyl red. This is another example, methyl red. Now methyl red, if we look on a table here of acid-base indicators, it's right here. We see it changes from red to yellow at about a pH of 4 to 6 or so. So I would expect methyl red to have a PKHIn right here in the middle, a little over 5, maybe 5.2, 5.1, something like that. That's our PKHIn. Okay, just from eyeballing it on that chart, because remember that PKHIn is when we're right in the middle of the color change, okay? The pH, we're right in the middle of the color change. So, I'm looking at this, and we see at very low pHs, 2 and 4, way below this PKHIn, we have a very red colored solution. And then at much higher pHs, or we're above the PKHIn, the dye is completely yellow, isn't it? So we do indeed see this transition from red to yellow, from the acid form to the base form. But there's this one interesting point that I guess I want to key in on right here in the middle. At pH 5. You see how it's kind of a different color there at pH 5? It's somewhere in between, isn't it? And that's because that pH is really close to the PKHIn. So at that pH, you've actually got this colored blend of both the acid and the base form. So it results in this intermediate color, doesn't it? Somewhere in between, it's an intermediate color. And that's actually very typical of these dyes. When you're working at a pH very close to the PKHIn, you've got some of the yellow form, some of this darker red-pink form, so you've got an intermediate, okay? So it's kind of very interesting. You can actually visually see converting the molecule from the acid form into the base form and vice versa. Now I mentioned that there are many different acid-base indicators available for our use. And that's certainly true. This is a table or listing of various different acid-base indicators which are known and oftentimes employed in lab. What's nice about this table is that you can see that not only are there multiple options, the names of which are listed here on the left. You don't have to memorize all the different names. But what I'd like you to do is a couple different things. One, realize that many different options exist. And these options are not the same, they're not equivalent. And the reason why is because different options change color at different pH ranges. So crystal violet will change color at very low pHs, from about 0 to 2, from a yellow to sort of a deeply colored violet. Thymol blue, from red to yellow, between about 1.2 to 2.7. Notice that also changes color at higher pHs as well. It's actually fairly typical. Several different dyes will do that. They'll have multiple pH range changes. But nonetheless, each of these different molecules change color at different pHs, and that's actually going to be pretty important. The second thing that I would like you to be able to do in interpreting a table like this is to be able to predict what color these indicators would be if you hold them at a certain pH. So in other words, let's consider this third one, erythrocin B. Well, that's probably a bad choice. Let's go to bromophenol blue. Okay, bromophenol blue. Its color change is from yellow to blue between 3 and 4.5 pH. If I take bromophenol blue and I put that in a solution that's pH 7, pH 7 is way out here, right? It's going to exhibit its blue color at pH 7. pH 6, it would exhibit its blue color because I've made the base form. In fact, all these higher pHs, it's going to be blue, the same color. Only if I go to a pH 3, pH 2, pH 1, then bromophenol blue is going to look like yellow in solution. Now what if I'm at a pH, let's say 3.6, 3.7. I'm somewhere right in between, aren't I? In that case, you get a blend of the colors, blue and yellow. So it might be a green color. So you have to kind of use your artistic interpretation at that point. But that's one of the major skills that we want you to get from this chart. Just be able to predict what color a particular dye would be in a solution at a particular pH. And if your solution is held at a pH which is above the PKHIn, it's going to exhibit the base color. And if your solution's pH is held at a pH below the PKHIn, it's going to exhibit the acid color. If you're right near the PKHIn, it's an intermediate color. And it's really as easy as that. Fortunately, there's many different acid-base indicators available to us. And the reason why that's fortunate is because we usually use these acid-base indicators for a particular purpose in lab. And that's for monitoring a titration reaction. If you're doing an acid-base titration in lab, you usually have absolutely no way to tell when the titration's done. Acids are clear and colorless, bases solutions are clear and colorless. When you react them, the solution's clear and colorless. So if you didn't use an indicator, you'd have no idea when the reaction's complete. So we are going to use indicators for our advantage, because indicators provide a visual reference for what the pH of the solution is. And that's very useful in laboratory chemistry. Okay? Now how do we use it specifically for a titration? Well, the good thing is that when we were computing pH along titration curves, we learned that a very large change in pH typically occurs at the equivalence point of a titration. We go usually oftentimes from very acidic conditions to very basic, or vice versa. But you get this huge change in pH right when you're at that equivalence point. Usually it's 3, 4, 5 pH units, maybe even greater. So what this means then is that if you choose an indicator that changes its color at that same pH range, you are in business, because what will happen is because when you reach the equivalence point, the pH of the solution will change dramatically. And if that coincides with the pH range of your indicator change, your indicator will change color at that point. And that's how we'd like to design all of our titrations, okay? We want to estimate what the pH at our equivalent point will be, and basically match that to the PKHInd. And if you successfully do that, you can use an indicator to signal the endpoint or equivalence point of a titration. To give you an example of that, let's go back to this slide about phenolphthalein that we were talking about earlier, okay? In this slide, what we're doing is we're titrating an acid and a base. Specifically, we're going to be titrating a weak acid with the base. Okay? So the initial pH, this is a titration curve, plot of pH versus the volume of the base added. So in this experiment, if you're not familiar with it, we have a long glass tube, that's our burette. And then down here, we'd have our weak acid sample. And inside the burette, we'd put our strong base, which is probably going to be sodium hydroxide or maybe potassium hydroxide. And this long tube, our burette, basically can add this solution into this weak acid. Meanwhile, I would get myself a pH meter and I'd measure the pH of this solution. So what I could do is I could make a measurement of the pH for every volume of my base solution added. And I could add half a milliliter, 10 milliliters, whatever it is. I can drain variable amounts in, okay? And then I can make a plot of the pH versus the volume. And this is, of course, called a titration curve. That's all it is. pH versus volume of base. Now, if I add 0 base, I haven't added any of this. I just got a solution of a weak acid down here. And because of that, the weak acid will donate some protons, making it acidic. So it makes sense I'm going to start off at acidic conditions, right? But then I'm going to start adding my base, and I'm going to start titrating the acid. I move through this region of the curve, which is called the buffer region. And eventually, I add enough base that I get to this very, very, very steep portion of the curve, right at 50 milliliters in this case. And that steep portion is my equivalence point. The steepest portion is always called the equivalence point and always coincides with the equivalence point. Now the thing is, if I didn't use any indicator, the beaker here would be clear and colorless the whole experiment. But I want a way to signal that endpoint. So I'm going to add some phenolphthalein to this mixture. Now earlier I said that phenolphthalein has a PKHIn right around 8. It goes from its acid to base form right around pH 8. Is that a good choice for this titration? I think it is. Look, our equivalence point is right here in the middle of the steep portion. Doesn't it look like the pH at that equivalence point is right between 8 and 9? So the pH jumps from, I don't know, pH 5 or 6 to pH 12 or so in just maybe 1/10 of a milliliter. And that corresponds to our equivalence point. And at that same pH range, our phenolphthalein changes color from colorless to pink. So when we were carrying out this experiment, the beaker would be clear and colorless, clear and colorless, clear and colorless, and then all of a sudden, we'd add a drop or two of our base from our burette into this mixture, and the color would suddenly change to a bright pink. And that would provide a visual indicator that this reaction had reached an endpoint, an equivalence point. We're done with the titration. Okay? And the reason why is because we neutralized all of our acid that was present, the weak acid in this original beaker. So by choosing this indicator, whose color changes at a pH very similar to the PKHIn, the color range of the indicator, we have a good match, and it changes color at exactly the right spot. So that's how you could use an indicator in acid-base titration.